Hello everybody, welcome back for Chem 103. I'm here in room Z351 if you want to drop by and say hello if you're on campus. Otherwise I'll see section 2 in about an hour over in lab. So today I want to talk a little bit more about some of these readings that you see here that are posted on Teams. I'm going to focus on just 2 of them for right now. And just kind of give you some of the highlights and why I chose these readings and what we can get from them, and also maybe a little bit of what we can criticize about them also. All right, so this first one I introduced a little bit before as the Richard Feynman. It was a physicist. He worked on the Manhattan Project. He won the Nobel Prize for his work in electrodynamics. And then as his life went on, he started being more involved in non-physics related things, such as this, where he's just sort of talking more generally about science. So let's take a look. All right. So he kind of goes through here and just says, you know, what's my business here? Why am I talking about this? Blah, blah, blah. So I want to go to just a couple highlights that help us with our definitions for this class and why we want to think about these things in this way. So first of all, when we talk about defining science, we talked a little bit about the process of science. What does it mean to do science? You've had a little bit of experience in lab now, working through some of those questions. I like the way that he talks about science to mean one of 3 things, so or a mixture of them. So kind of like separate things that are all called science. I think by talking about those 3 things, maybe we can deconvolute them a little bit and deal with some of the confusion. All right, so the first thing sometimes is a special method of finding things out. And this is kind of what we talked about last week in lab. The idea that you experiment, that you start with a hypothesis, but you leave that hypothesis open to uncertainty and doubt, and you propose experiments, and you look at the data, and then you refine your hypothesis. The way that you observe things, you make observations, which you could potentially collect into laws, and then eventually you can come up with a theory that you can try to prove or at least support with evidence as to why those things are happening. So that's the scientific method. That's kind of doing science. Science sometimes also means the body of knowledge that you get. So that's another source of confusion. Is science the thing that you're doing, or is science, like when we talk about science class in school, it's the particular material that you're learning, which is different, I would say, from the process of finding those things out. And then third, in society, when we think about science, we often, maybe most, think about the new things you can do when you have found something out, which is really technology, or what we might call engineering. So we've done all these experiments, figured out how something works, come up with this great working theory of why this system does what it's supposed to do, and then we can use that to come up with new technologies that utilize those things. So that is actually kind of a separate thing. That's really not science. You know, building a battery from chemistry is an interesting challenge, and it's engineering, but it's technology, but it's not really science. You've already sort of found out how these things work. You're just trying to get them to work together. And so thinking about those as 3 sort of separate ways of defining science can be helpful, because they really are different things. So the Feynman here has some special things to say about technology, because he saw the Manhattan Project, which was the project to develop nuclear weapons during World War II. And many of the scientists, including Dr. Feynman, were really uncomfortable with what came out of that. The idea that they were studying this interesting thing and coming up with these interesting things that had never been done before, understanding how atoms are put together and how atomic structure worked was really exciting to them and something they wanted to work on. And then they saw the great amount of death and destruction that came about as a result of their work. And they wrestled with that in some different ways. And so for Feynman, he took a kind of a hands-off approach. So he says, the power to do things carries with it no instructions on how to use it, whether you use it for good or for evil. So he's saying that, when we find out new things about science and then we use them for technology, it's not really the scientist's responsibility there, because it could kind of go either way. And so he tells the story, which he was kind of famous for being kind of a storyteller, so we don't really know if this is true or not. But he said that a man told him in a Buddhist temple, "To every man is given the key to the gates of heaven. The same key opens the gates of hell." And so his ideas here are that, as you can kind of tell from that something of great power can cause harm as well. Kind of the Spider-Man thing, right? With great power comes great responsibility. So as we find these things out as a society, whose responsibility is that? And so he says here, shall we throw away the key and never have a way to enter the gates of heaven? Or shall we struggle with the problem of what's the best way to use the key? And so he says that you can't deny the value of the key. So to him, it's not the scientist's responsibility to, explore some things and not others, or to think about the potential negative effects of what they're exploring. To him, you have to explore this stuff, and then it's up to society to come up with rules and restrictions and laws and whatever else to try to put these in a good direction, try to point them in a good direction. All right. So then he kind of relates this to science and society. So he says, if you work to develop nuclear energy, you must realize that it can also be used harmfully. Therefore, you would expect that in a discussion of this kind by a scientist, this would be the most important topic, but I will not talk about it further. Right? So he's saying, this is not a scientific problem. This is a social problem. How do we prevent people from, killing each other with more and more powerful weapons? It's not the scientist's problem to decide whether or not to develop those things. I'm not saying he's right here. This is something that you can think about and come to your own conclusions. I think that in the years since this, so the almost 50 years or so, I don't remember the date actually. Is it more than 50 years? I don't have the date on here. It was in the 60s. So, yeah, more than 50 years. I think those ideas have changed a little bit, and scientists are more socially aware and are thinking more about whether what they're doing is really helping society or not. All right. So let's look at some of the other stuff So that's kind of the technology piece, the things that have been found out. Then second is the things that have been found out. I would encourage you to read this and talk about like the amount of knowledge that has been found through this method. Again, he's writing from a position of a scientist, a white scientist in the 1960s. So I would encourage you to contrast some of the things he's saying with some of the material in the other reading talking about indigenous science and indigenous knowledge. That getting knowledge through different sources aren't necessarily always in conflict. I think some of the most beautiful stuff that he talks about here is the last part, the method of finding things out. All right, and he, in this part, has some really nice definitions that you can use when you're trying to clarify your knowledge on these ideas. So, for example, he says, the method is based on the principle that observation is the judge of whether something is so or not. Right? So you have to observe, make measurements, whatever. Observation doesn't just mean seeing with your eyes. It can mean any kind of detecting, right? And then you use that as evidence to decide whether something is so or not. So that necessarily excludes certain types of knowledge. And I think that's important, that the scientific method is not meant to apply to every possible thing that you could find out. And there have been a lot of examples in history where the scientific method is applied and then it sort of fails because of the observations aren't really possible, or the standardization is not really possible. So sometimes when we look at how the scientific method is used, for example, in the social sciences, where you're dealing with people, so you're dealing with huge amounts of variables that can almost never be fully controlled, things like education. Now you sometimes have problems, and the scientific method, it doesn't indict the method, it doesn't say the method isn't good, but it might not really be applicable to those situations. And so the other important point here is he says that prove in this context really means test. We talked a little bit about that last week, that when we prove something in science, it doesn't mean that we have absolutely, that we now have absolute faith in its truth. It means that we test it and test it and test it and test it again, and if it keeps passing those tests, then it's most likely that that's the correct explanation. And he talks about how these exceptions are interesting because they show the old rule is wrong. And so when you find exceptions to something, you can then try to refine it. And chances are that the exceptions don't totally invalidate everything you did before. The exceptions help you refine your model so that what you maybe overgeneralized before, you have to now narrow down to be a little bit more specific. All right, and so this is, again, kind of what I was talking about before. The principle that observation is the judge imposes a severe limitation on the kinds of questions that can be answered. You can pretty much just say things like, if I do this, what will happen? Questions like, should I do this, and what is the value of this, are not of the same kind. So, you can't really use the scientific method to decide if you love someone, or if you, if something is a good idea or not. And so sometimes we use the scientific method in those situations anyway, and we come up with something that sounds science-y, but it isn't really, because it wasn't meant to be that in the first place, right? So a good example is what we talked about last week with respect to grading in classes. You can assign numbers to grades, and you can calculate averages and standard deviations and do tests and things like that. And it feels very measurement, feels very science-y, feels very, I'm testing what you're learning. But in reality, it's really not, and there's a lot more variables there, and it's really not a scientific question in the first place, or it may not be. The other side of this is often in society, in the news, we find things that very clearly are scientific questions. Does this exist or not? Is this real or not? Is this happening or is it not happening? Things, did this happen or did it not happen? These things can be shown with evidence, and yet ideologically people can still choose not to believe them. And so that introduces a tension with society as well. If we're saying, look, we can ask this question, if I do this, what will happen? We can show through experiments that when I do this, this is what happens. And then people can still say, nope, I don't buy it. And so that's one of the important things that we want to think about, is how can we really understand what types of things we can explain or we can find out through these methods, and what types of things are beyond these methods. All right. So another thing that happens here is some misunderstandings or some misapplications of the scientific method, which I think Feynman does a nice job of giving some examples. Interpreting results. So to take a trivial instance, there's a famous joke about a man who complains to a friend of a mysterious phenomenon. The white horses on his farm eat more than the black horses. He worries about it and can't understand, and his friend suggests maybe he has more white horses than black horses. So not looking at all of the possibilities, being too narrowly focused on a particular result, can lead to some problems. And then he actually has a really important point here that it seems like he kind of just glosses over and goes on. But when people say things like, well, my sister had a cold and in 2 weeks, I think what he's saying here is that we often fall into these traps of reasoning where we're highly affected by circumstances and circumstantial evidence, where we say, well, you know, my mom had a cold and she took vitamin C and she got better in 2 days. So, you know, vitamin C fixes colds. But, and this is actually true, if you look at the scientific literature, it has been studied over and over and over again, and vitamin C has no effect on any illness. Other than if you don't get any vitamin C, you could get scurvy. Anything else, it has no effect at all. Your body just excretes it if you take too much vitamin C. So all of the, you know, extra vitamin C supplements are all nonsense. This has been shown over and over again in major scientific studies. But people will still say things like oh yeah, my mom takes vitamin C, she never gets sick. Where clearly there's other things going on there, other factors. All right, he talks a little bit about objectivity. And so I would recommend you take a look at the rest of this. Oh, there were a couple other things I wanted to point out here before we go on. So it was thought, so one thing we talk about is these different ways of getting knowledge. And the scientific method, remember, we talk about it as just this thing in this class, but at one time it was highly controversial. And sometimes in some pockets of society now, it still is highly controversial. The idea that you do not need authority to get knowledge. So, you know, if you look back in the Middle Ages, before the scientific method, in Europe, how did people get their knowledge? Well, I mean, certainly probably people were doing something resembling science. We know that indigenous populations were doing that for thousands of years. But in those societies, it was primarily based on authority. The Pope or the king or whoever would say, this is so, and the people would say, okay, that's the truth. So science is necessarily and importantly anti-authoritarian, because anybody can do experiments and find out the information for themselves, and they don't have to believe what the person in authority is telling them. So, you know, in authoritarian societies, the idea that people can come up with their own methods of knowledge acquisition is a danger to the regime. And so, as he says here, authorities lose some of their authority. So authoritarian societies are often necessarily anti-science because of that, because they know that if people are making their own investigations as to what's true and what's false, then they aren't going to listen to whoever is in charge anymore. All right, I'm trying to remember if there's anything else I wanted to talk about here. Okay, well, I would recommend reading it. It's a pretty easy read. It's interesting, and it's worth your time as you think about these ideas. All right, moving on to the next thing. Sorry, I should have organized this better. Okay, this one is a little bit drier, a little bit more about, you know, kind of the general process of science. So a couple things to note here. First, there are some assumptions behind science. One assumption is that things actually are consistent and comprehensible, right? So things are actually knowable. Is that a word? Knowable? We presume that things and events in the universe occur in consistent patterns and that we can understand them if we go through carefully. That also kind of assumes then that the universe is a vast single system in which the basic rules are everywhere the same. So if we think about how we measure gravity on Earth, that should also apply elsewhere. And of course, we can do those measurements and find that that's true. So then we make that assumption elsewhere. And then when things seem to not fit that, we have to revise some things. And then, although scientists reject the notion of attaining absolute truth, we talked about that a couple times now. We're not going toward absolute truth. We're not trying to find something that must absolutely be true forever with no possibility of being false. We're simply testing things and getting more and more certain of a result. So decreasing uncertainty as we learn more until we decide that we pretty much are good with that. But what we should say here is most scientific knowledge is durable. So I don't want you to get in this kind of contrarian mindset of like, this happens like on YouTube and other social media a lot, where somebody says, well, this one little thing doesn't quite fit this rule, so therefore the whole thing, we have to throw the whole thing out, it's all garbage. That's not how science works. Right? Scientific knowledge is mostly durable. All these tests over and over have been done over and over again in different contexts. Those are still valid. When we find counterexamples to our rules, that leads to modifications of ideas. So maybe something is too general, maybe something hasn't quite been explained yet, maybe we haven't gotten to something yet that we need a little bit more powerful instrumentation first before we can get to that. So as the example, we said the Newtonian laws of motion, when Einstein talked about relativity, it doesn't mean that those laws are invalidated completely. It just means that they don't work in particular domains, and we have to use something else there. Right? So NASA uses Newtonian laws in calculating satellite trajectories because those work fine, and when we're sending spaceships out places and whatever. But if you're talking about black holes colliding or something, or electrons moving around, you have to use some different laws of motion, some quantum or relativistic type things. And then, as Feynman said also, there are many matters that cannot usefully be explained in a scientific way. So the scientific method is only applicable to these things that can be shown or questioned in a particular way. Does this happen? Is this a cause and effect relationship? Does this exist? Does this not exist? But beliefs, personal beliefs, like the purpose of life, is not something that is a scientific question, really. It's not meant to be answered in that way. All right, so some more information about what scientific inquiry looks like and how you investigate things with evidence. And then this is an older text, but this is something that's been developed more and more. And if it's something that interests you, I would encourage you to look up Science and Technology Studies, which doesn't mean like studies, like research studies. It's a sub-branch of philosophy, actually, that deals with some of these assumptions in science and some of where science goes wrong and how science gets things wrong, particularly with regard to power structures. So for example, there's a good example in here. When the science is done primarily by one type of scientist, so studies of primates by male scientists, they kind of just ignored female primates' community building behavior, right? When mostly white European scientists came up with race science in the late 1800s, early 1900s, so eugenics, social Darwinism, things like this, they were applying the scientific method to come up with this idea that the races are different, and that humanity can be separated into races biologically, and there is a hierarchy there of more intelligent, more advanced races and less intelligent, less advanced races. And we know now that's complete nonsense, and now we can really even prove that with DNA. We can show that race is not a biological construct, it's a social construct. But at the time, it actually took activists and scientists who were not part of that community pushing against these ideas for the scientists to revise their positions. So race science was mainstream science in the early 20th century. That's what, like if you go down to the Field Museum in Chicago, look at who the president was in the early 1900s, the presidents. These were people who were in the forefront of race science. Same with the Museum of Natural History in New York City. So even though we know now that's all garbage, that was mainstream science. And so sometimes it takes people pushing from the outside to change the way that people think about these things. And to think about that bias. All right, well, it's about 1:30 now. I don't want to ramble on for too long, but take a look at all of these documents. They're all worth your time to read. They'll all help you to meet those objectives around understanding how science works and the scientific method. So lab today for section 2, we'll be doing investigation of matter and paper chromatography, so some more chances to use your scientific skills. And then next week, there are no labs on Monday or Wednesday. Monday because of Labor Day, and Wednesday because we're doing these one-on-one meetings instead. So make sure that you sign up for a time to do that next week, and we'll meet and see your progress so far. Again, just as a reminder, the module reflection from this module 1 is due this weekend so that we can talk about it next week. And make sure that you have all of your stuff that you've done, so your lab notebook and whatever notes you took on the readings or writings or other things that you did, so that we can discuss next week. So I will see section 2 in about half an hour. Section 1, I will see you at individual meetings next week, and as a whole then in lab for the chemical reactions lab in 2 weeks. As usual, let me know if you have any questions, and I will talk to you all soon. So thanks, bye.